related rates are when you're looking at how an equation is changing with respect to time. It's always nice to know, for instance, if there's a tanker that's leaking oil, how fast the area of the spill is changing with respect to the radius, but that's probably not what the public wants to know. They want to know how fast the spill is changing with respect to time, how much oil is leaking out after an hour or a day or a month. So when we look at related rates, that's what we're looking at, how things are changing with respect to time. Well, when we look at a normal equation, let's take that area of a circle. We've got the area equals pi r squared. Okay. When we look at that equation, there is no t variable in there. There's no time. So when I differentiate that, you are going to have a differential for both of those. So what that means is whenever you take the derivative of a, you're going to have a dA dt. Whenever you take the derivative of r, you're going to have a dr dt. Everything is going to be dependent on that time variable. Not a big deal. You've got dA over dt, dr over dt, but everything else stays the same. Once you differentiate, you're going to be plugging in values. Just to kind of make this a little bit easier, whenever you're plugging something in for a rate of change, dA over dt, dr over dt, that is how something is changing with respect to time. So dA over dt is going to have a unit that is a square unit of length per time. This is your numerator, which is that A. This is your denominator, which is that dt. So you're going to be looking for meters squared per second or miles squared per hour. That's going to help you figure out, what am I going to plug in for dA over dt? Well, you're going to look for those units to help you figure out, is this the change or is this the actual area? Likewise, dr over dt, you're going to have a unit of length per time because it's radius, so you may have just meters per second or feet per minute. Okay, so let those units help you figure out which item you're going to plug in. Well, we have a game plan for solving related rates. As with any word problems, the very first step is to read the problem. Read and reread. So read the problem just to kind of get an idea of what's going on, and then reread the problem again to see if you need to draw a picture, what's going on in the problem, etc. If you need to draw a picture, great. If you don't, that's fine as well. With that picture and looking at the problem again, you're going to try to figure out what equation is going to fit in there. So look for some key words: circles, area, volume, spheres, those kind of things. Ladders leaning up against buildings, those are always right triangles. After you find your equation, you're going to differentiate with respect to time. Remember, you have a d, whatever your variable is, over dt. So everything is going to need that little crutch because every variable is going to be dependent. After you differentiate, then you plug in. Notice, you differentiate, then you plug in. Let's see how it's going to look. These are fascinating problems, by the way. Just wait. Example 1. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? Oh my goodness, that is so exciting. So you read the problem. When you go back up, you see those key words: circle, area. That's going to lead you to your equation. Area of a circle, pi r squared. I want to differentiate with respect to time. The derivative of area, or A, is 1 dA dt equals the derivative of pi r squared is 2 pi r dr dt. Remember, pi is not a variable, it is a value. We actually want to solve for dA dt because it asks for what rate is the total area changing, so we want to know dA dt. When we look up there, we notice that we want to know what's going on when the radius is 4 feet. Notice this is not a change in time, so it's going in for the R. When we look at the other values, you've got radius is increasing at a constant rate of 1 foot per second. Because you've got that foot per second, you know that's going in for dr dt. And then of course we want to multiply that together. Make sure we have our units on there. dA, that's area, so that's going to be feet squared. Time is seconds. So we've got our units on there and we've got our answer. Remember, we'd like to keep these as simplified as possible, so keep the pi if you can, keep radicals if you can. If not, make sure you round to 3 decimal places. Okay, let's look at our next example. We have air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So they're talking about a spherical balloon. Now, I know some of you more argumentative students are thinking, a spherical balloon, there's not a balloon that's a perfect circle. Well, we've got to take baby steps. We're going to have these nice, pretty geometric shapes. We're not going to think about friction at this point. There will be plenty of time for us to think about friction and the fact that not all balloons are perfect spheres. So we're just going to kind of deal with things in their most simplest form. So if they say it's a sphere, we're going to say it's a sphere. That tells us its volume, but so does this, cubic feet per minute. It's a cubic unit. That also tells us volume. Well, the volume of a sphere is 4/3 pi r cubed. We want to differentiate with respect to time, so the derivative of v is dv over dt. The derivative of 4/3 pi r cubed, r is the only variable, so bring that 3 down in front. So that's going to be 4 pi r squared dr dt. They tell us that the volume is changing at a rate of 4.5 cubic feet per minute. Even though 4.5 is perfectly fine, I'd rather keep it as a fraction. It just makes me happier, and you all know how much I love me some fractions. 4 pi, we know that we want to know what's going on with the change of radius. Remember, it says change of radius, rate of change of radius. That tells us dr dt. What we have is the radius. We want to know when the radius is 2. So 2 squared, we're trying to find dr dt. So we're going to divide through. We've got 4 pi times 2 squared, so we have 16 pi. Divide by 16 pi, so we end up with 9 over 32 pi. That is our perfect value. This is dr over dt, so remember our units are feet per minute. This is what our dr over dt is equal to. Let's look at another example. Now, example 3 is really neat because you've got a cone. When you think about the equation of a cone, you've got v equals 1/3 pi r squared h. Now, what's kind of unique about this equation is that you have 2 variables on the right side. If I leave both variables, I'm going to need to do the product rule. When I read the problem, it says a conical tank with vertex down is 10 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. Notice they talk about volume, 10 cubic feet per minute. They talk about h, that height or depth, same thing. They do not mention the radius. So there is no r or dr dt mentioned, so that means you have to sub it out. We won't be dealing with the r and the h at the same time. Well, when you look at a cone, remember, is proportional. The radius over the height is going to be the same proportion all the way through that cone. They do give us some information about this. Let me change my color to red. So let's look at this proportion. They do tell us 10 feet across the top and 12 feet deep. Well, 12 does correspond to the height. The radius, however, is not 10. 10 would be the diameter, so the radius is 5. If I want to sub that radius out, that means I need to solve for the radius, which means R is going to equal 5h over 12. Okay, so this is what we're going to substitute in right here. My new equation, let's change this to black. Volume equals 1/3 pi. R is 5h over 12. That's going to be squared times h. If I want to simplify that a little bit more, I'm going to have 1/3 pi 25 over 144 h cubed. Now it's going to seem kind of goofy, but I'm going to leave it as 1/3 times pi times 25 over 144 h cubed. Because when I take the derivative of v, dv over dt, when I take the derivative of this side, that 3 is going to come down and cancel out that 1/3. So it just kind of makes it a little bit easier. Why multiply them together if you're going to have to divide it back out? So we end up with 25 over 144 pi h squared dh dt. And notice we have everything now that we need. We want to find the rate of change of the depth, so we want to find dh dt. dv dt is 10 cubic feet. And once again, I know that's going in for dv dt because look at your units. That's going to be 10. And they tell us the depth of the water is 8 feet. So I'll plug that in. And then I'll solve for dh over dt. Well, when I plug all that in and I divide by my 25 divided by 144 pi times 64, that's going to leave me with 9 over 10 pi. Once you simplify, it's dh over dt, so the units on your height are feet, the units of time are minutes. And you can plug it in your calculator. Just leave your pi out of it until the very end. Okay, examples for you. I'll be waiting on video 2 to help you with that.